Hi, I am Prabhat Kumar Chand from Indian Statistical Institute, Kolkata, India, going to present our ALGOWIN paper Run for Cover Dominating Set via Mobile Agents. It is a joint work with Anisur Rahman Molla and Sumati Siva Subramania. A dominating set D of the graph G is a subset of the nodes such that for any node in the graph, either it belongs to D or the node has a neighbor in D. In the following figure, the black colored nodes represent the dominating set for the graph. The dominating set problem is a classical and well studied problem in the classical graph theory, and there has been a few studies on the dominating set and related problem on the local and congest distributed models. Our paper is the first attempt to solve the dominating set problem in the mobile robot model. Finding small dominating set using mobile robots could be useful in the following scenarios. A minimum dominating set can form the charge station or parking places for the autonomous mobile robots represented by the cars. It can also be used in the guarding problems like the famous art gallery problem. Also, they could be useful for identifying crucial nodes in a network or designing secure system for electrical grids. Now we come to our problem definition. So we consider an undirected connected n-node simple anonymous graph G with n mobile robots placed arbitrarily over the nodes of G. Let delta denote the highest degree of the node in a G. For our first problem, the robots, irrespective of their initial placement, rearrange and color themselves in such a way that there is a robot at each node of G and there is a self-identified subset of the robots which are colored black, which represents the minimal dominating set for G. For our second problem, we consider the approximate minimum dominating set where the robots, irrespective of how they are initially placed, rearrange and color themselves in such a way that a dominating set for the graph G of size at most alpha times the optimal is identified. Here D star represents the minimum dominating set and alpha is the approximation ratio to the minimum dominating set. So our goal will be to design the algorithms for solving these problems as fast as possible, keeping a low memory per robot and keeping the approximation ratio as small as ln delta. So these are our results. So our first algorithm, where the robots begin at a rooted initial configuration, produces both minimal dominating set and a maximal independent set in order of m rounds, where m is the number of edges of the graph. Our second algorithm, where the robots begin at an arbitrary configuration, it also produces both a minimal dominating set and a maximal independent set in order of L delta log lambda plus NL plus M rounds, where L is the number of initial clusters of the robot in the arbitrary configuration, lambda is the ID of the highest ID robot, and N is the number of robot as well as number of nodes in the graph, and M is the number of edges. The final algorithm, which produces an Ln delta approximate minimum dominating set, takes N delta log lambda rounds, and the robots begin at an arbitrary configuration as well. So for our model, we consider the underlying graph to be simple, connected and undirected with n nodes and m edges. The nodes are anonymous with no labels and are memoryless. The ports on each node has a port numbering from 1 to delta, where delta is the degree of that node, and each edge receives two independent port numbering at either end, and we denote the maximum degree of a node in the graph by delta. So there are n robots residing on the nodes of the graph, with each robot having a unique ID and with the maximum ID of the robots being lambda, and the robots can only communicate with co-located robots, that is, they can transfer information with other robots only if the robots are present at the same node, and the robots cannot reside on the edges. The robots operate in synchronous rounds, and with each round consisting of a communicate, compute and move episode, where the robots can communicate with the co-located robots based on the communication, can compute something and decide to move via a particular port. For the time complexity, we are taking the number of rounds required before terminating as the time measurement, and for the memory complexity, we are taking the number of bits required at each robot to execute the algorithm. Now before explaining our algorithm, let us describe some of the important related works. See, in the first paper, an efficient distributed algorithm for constructing small dominating sets by Lijun, Jia and others, they gave the first efficient distributed implementation for finding small dominating sets in the congest model and provided a ln delta minimum dominating set in order of log n log delta rounds, where n is the number of nodes and delta is the maximum degree among the nodes. In the second paper, what cannot be computed locally by Fabian Kuhn and others, the authors established time lower bounds for finding a minimum dominating set in the context of classical message passing distributed model. They also showed that any algorithm can produce at most delta to the power 1 by k approximation in k rounds. In the third one, named the deterministic distributed dominating set approximation in the congest model, the authors provided a deterministic approximation algorithm for the minimum dominating set problem in the congest model with an almost optimal approximation guarantee in 2 to the power order of square root of log n log n rounds. They also explored the problem of connected dominating set. Recently, the paper Distance to Dispersion with Further Constant by Tanvir Kaur and others introduced the distance to dispersion problem in the context of the mobile robots, which is a closely related problem to ours. So they showed that with order of log delta bits of memory per row, the D2D problem can be solved in order of m delta rounds. Additionally, they showed that if the number of robots is greater than the number of nodes, the nodes with the shuttle robot form a maximal independent set for G. So these are the main challenges of designing algorithms in our model. So the robots cannot communicate globally or have any topological information about the network, and the memory of the robots is limited, so they cannot store sufficiently large information, like they cannot store the map of the whole graph. And there is a lack of centralized control on the movement of the robots, and as we have already seen, the nodes are memoryless and so they cannot be marked or cannot be labeled in some way, and the robots are initially placed arbitrarily across the graph, so there is also an issue of communication between the robots. This is our roadmap for the presentation. So we will first describe an algorithm where the robots compute a minimal dominating set with robots starting at a single node, which is called the rooted initial configuration. Next, we extend this algorithm and compute a minimal dominating set for the robots present arbitrarily as multiple clusters. And finally, we give a ln delta minimum approximation algorithm for the robots. First, let's get started with the rooted initial configuration. In the rooted case, we assume that all the n robots start at a fixed node called the root. In the given figure, we consider A to be the root where all the n robots are initially residing. The minimum ID robot at the root first settles down and colors itself as black. Then the robots explore the graph in a DFS manner, settling a robot at each empty node one by one and coloring itself as gray or black. So whenever a new robot settles, it checks its neighborhood for a black robot, and if it finds a black robot, colors itself as gray or otherwise colors itself as black. So a robot which is coming from a black parent can immediately color itself as gray. Now in the following figure, as we can see, the algorithm start at the root A where the first robot is colored black. The robots slowly explore the graph in a DFS manner sequentially, settling one robot at each step and coloring the robots accordingly. Now the algorithm stops when all the n robots get settled and each robot in the graph receives either a color black or gray. In the final configuration, as you can see, all the robots have settled and each robot is either colored black or gray. In this final configuration, the black colored robots represent the minimal dominating set for the graph. So for the analysis, first we note that the DFS for the robots take order of m rounds, and with each step of the DFS, the robots can take additional of order of delta I rounds to scan their neighborhoods before coloring a robot black. Here delta I is the degree of the current node. So the overall round complexity boils down to order of m rounds, and the memory complexity is order of log n bits per robot. Now, as you can see that in the algorithm, no two robots can be colored black if they are adjacent. So the dominating set also represents a maximal independent set as well. Now we move to the arbitrary initial configuration of the robots. In the arbitrary configuration, the n robots are placed arbitrarily across the graph as clusters. The algorithm runs in 3 stages. In stage 1, first the robot disperse, that is, they rearrange themselves in such a way that there is exactly one robot at each node. In stage 2, a leader robot is elected, and in stage 3, the leader robots then finds the minimal dominating set for the graph. In the first stage, with robot being present arbitrarily across the graph in small groups, first follow a dispersion protocol, after which they resituated themselves in such a way that there is exactly one robot at each node. Dispersion leads to the creation of multiple, here we consider L, independent DFS trees. Each of the n robots belongs exactly to one DFS tree. Now for stage 2, we want to elect a leader robot. For a leader election, the robot must communicate with each other and select a leader. But since we have no movement synchronization, there is a problem. As we can see in this figure, whenever a robot from node 6 jumps to communicate with a robot at node 2, at the same time, the robot at node 2 can also jump out and move to node 1. Therefore, the robot placed at node 6 may not communicate with the robot present at node 2. So, how can we guarantee that each robot can communicate with other robots so that a leader can be elected? So, with the intention of guaranteeing communication between the robots, we introduce a procedure called the procedure MYN. The acronym MYN stands for Meet Your Neighbor. For procedure MIN, the robots explore the ID bits. Each ID bit is associated with a window of delta round. In the first delta round, the robots check their rightmost ID. If the rightmost ID is 1, they visit their neighbors and comes back and communicates with any robots that are present in their neighbor. And if the ID bit is 0, they stays back to their original node for delta rounds. In the next delta rounds, the next ID bit is checked, and similarly if the ID bit is 1, the robots again visit their neighbor and back, and if the ID bit is 0, the robot stays back for delta rounds. As we can see in this example, in round 1, the robots 1, 3, 5, 7 and 9 move and communicate with its neighboring robots, while the robots 0, 2, 4, 6 and 8 stays back for delta rounds. In round 2, the robots 2, 3, 6, 7 are activated, and now they move and communicate with its neighbors, while the rest of the robots sit back for delta rounds. So since the maximum ID of a robot can be lambda, so by the end of order of delta times log lambda rounds, each robot Ri is guaranteed to communicate with its neighbor Rj. So this is the pseudocode for procedure MIN, where at each window of delta rounds, a robot either visits all of its neighbor or remains at its current node for delta rounds. So each robot is guaranteed to meet all of its neighbor robots in one execution of procedure MIN, which takes order of delta log lambda rounds. Now for the leader election in stage 2. So during DFS, multiple DFS trees are created, with each tree containing the DFS identifier information, which is the lowest ID robot in the DFS. So using procedure MYN, the different DFS trees can communicate and select the lowest DFS identifier information. The robot that corresponds to the lowest DFS identifier information becomes the leader robot. Now, once the leader robot is selected, we move to stage 3. In stage 3, the leader robot art star identifies its own node as the root and initiates a DFS from the root. The leader robot colors itself as black and it constructs a single DFS from the roots as it realigns the pointer information at each robot and consequently color each robot as gray or black exactly in the similar procedure as with the rooted case. In the final configuration, the black colored robots represent the minimal dominating set and the maximal independent set for the graph. Now for the analysis of the arbitrary case, in stage 1 dispersion take order of m rounds, in stage 2 the leader election takes order of L times delta log lambda plus n rounds, where L is the number of robot clusters at the start and lambda is the maximum ID of the robots. Finally, the dominating set identification takes another order of m rounds as it runs similarly to the rooted case. Therefore, the overall time complexity becomes order of L delta log lambda plus NL plus m rounds. The memory complexity remains at order of log n bits per robot. So, similar to the rooted case, the dominating set here also represents a maximal independent set as well. Now, we come to our ln delta approximation algorithm. Now, in some particular graphs like the star graphs, so if you apply our previous rooted case algorithm, so for example, consider this star graph where all the robots are initially beginning at the root node A, and then if we apply our existing rooted case algorithm, then we end up having a dominating set where all the leaf nodes are in the dominating set while only the center node is covered. However, the optimal dominating set should have been the opposite. So if in the optimal dominating set, only the middle node should have been the part of the dominating set, while that middle node could have covered all the leaf nodes. So for this reason, the one hop approach can give a large dominating sets than the optimal. So we modify our algorithm to introduce a new approximation algorithm that gives us a log delta approximation to the minimum dominating set. So in our approximation algorithm, a robot can receive one of the three colors. So it is a black if it's a member of the dominating set, it is gray if it is covered by some dominating set, or it can be white if it is uncovered. We also define span of a robot to be the number of white neighbors of the robot including the robot itself. So our algorithm runs in iteration, where in each iteration each robot Ri does the following. So first it calculates its span, then it gets to know the highest span value among its immediate neighbors, then Ri gets to know the information of the highest span among its two hop neighborhoods, and if Ri is the robot that has the highest span among its two hop neighbors, then it can color itself black and then move to inform its white neighbors to color themselves as gray. So the process continues till there are no white robot left. And to communicate, like to get the information from the neighbors and the two hop neighbors, the robot uses the similar procedure MYN as defined earlier for each communication round with its neighbor. Now for the analysis of our approximation algorithm. Span calculation, knowing the highest span among the immediate and two hop neighbors, and coloring of the robots uses procedure MIN for communicating between the robots, which take order of delta log lambda rounds. And in the worst case, each iteration can lead to the coloring of a single white robot. Therefore, in the worst case, the algorithm can run up to order of n iterations. With the robots now scanning its two hop neighborhoods, the algorithm produces an ln delta approximation to the minimum dominating set, and therefore the overall round complexity comes to order of n times delta log lambda rounds, and the memory complexity remains at order of log n bits per robot. So to conclude, we present the following two theorems. Let G be an n-node anonymous graph with the maximum degree delta. Let n mobile robots with distinct IDs in the range 0 to n to the power c, where c is a constant, be initially placed arbitrarily among L nodes of G in L clusters. Then a minimal dominating set and a maximal independent set for G can be found in order of L delta log lambda plus NL plus m rounds using log n bits of memory per robot, where delta is the maximum ID of the robots. Secondly, let G be a n-node arbitrary connected and anonymous graph with a maximum degree delta. Let n mobile robots with distinct IDs be placed in a dispersed initial configuration. Then a ln delta approximation solution to the minimum dominating set for the graph G can be found in order of n delta log lambda rounds with order of log n bits of memory per robot, where lambda is the maximum ID of the robots. As future works, it would be interesting to explore the lower bounds for the problem, both for memory and time complexity and the number of robots used for solving the problem. On the other hand, it would also be interesting to investigate the problem in context of the faulty robots. Thank you very much.